So good afternoon to everybody. Good morning or good evening, depends on where you are in the world. So today we are going to have our last CASS talk of this year. So with a very special talk by Professor Valeri Mladenov from Technical University of Sofia in Bulgaria, talking about introduction to Memristors and Memristors neural networks. So Professor Valeri is a head of the Department of Fundamentals of Electrical Engineering and head of the Neurocomputing Laboratory of Technical University of Sofia. Professor Mladenov's research interests are in the field of electrical engineering, electronics, automatic artificial intelligence, and neural networks. He has more than 350 scientific papers in professional journals and conferences. As a member of several editorial boards, Professor Mladenov serves as an editor-in-chief, associate editor, and review for a number of professional journals and conferences. He's a senior member of IEEE, chair of the Bulgarian IEEE Joint CASS and Solid-State Secret Society chapter, and a member of the IEEE Sequencing Systems Technical Committee on Cellular Nonlinear Networks and Memristors Array Computing. He is also a senior member of the International Neural Networks Society, member of the International Council of Large Electric Systems, member of the management boards of the Scientific and Technical Union of the Power Engineering and the Union of Automation and Information in Bulgaria and others. So thank you very much, Professor Valeri, to accept our invitation to close this season of CASS Talks. So now the floor is with you to start your talk.
Okay, good afternoon, everybody. Good morning, good evening, depends where you are. In fact, not I'm in Bulgaria, I'm in Greece now, but it is 6:30 p.m. So good evening, probably, for the people in this region. I would like to thank Professor Reis for inviting me to give this talk. It was meeting between us, and when I told him that I work with Memristors and especially applications in neural networks, he was interested and invited me to give this talk. I came from Bulgaria. You've heard my main details. I'm, in fact, a circuits and systems guy, member of IEEE, more than 8 years, I couldn't remember now. And last, let's say, 20 years, I deal with Memristors. I don't know how many knows about Memristors, but if you know about Memristors, you may skip the first part of the talk. Outline the talk in this way. First, I'll do a short introduction to Memristors for those who are not acquainted with them. Then, especially, I'll talk about Memristor modeling because this is my area of interest. I'll describe some standard Memristor models and some modification of these models that my team did. And then I will talk about applications, especially application in neural networks. The first three applications that are very interesting, I'm going to skip. This is a general type of applications, but I'll discuss about applications in neural networks, and I'll finish with some conclusions about this regarding to this talk. Now, let's start. What is a Memristor? You know, the main electrical quantities are voltage, current, flux, magnetic flux, flux linkage, or flux simply, and electric charge. And the connections between them are given in the picture. The three main passive circuit elements, resistor, capacitor, and inductor, capacitor connects charge and voltage. Inductor connects flux and current, and resistor voltage and current. And what is the missing is the link between the charge and flux. This was since 73, and then in 73 appeared the famous paper of Professor Chua, Memristor, the missing element, the missing circuit element. Oh, sorry, 71. And in this paper, Professor Chua predicted Memristor theoretically, presented some models, but real device was not yet developed, like a simple device like resistor, capacitor, two plates with the electric between them, an inductor like coiled wire. But because of this, it was silent period in Memristors. But 2008, the famous paper of Stanley Williams from Hewlett-Packard, the missing Memristor found, paper in Nature, where he presented the first Memristor, titanium dioxide Memristor. He presented a device that behaves like a Memristor, like predicted by Chua Memristor. And since 2008 up to nowadays, the big development in Memristor area with many applications. So this link was given first by Professor Chua. What is a Memristor? Memristor, the acronym comes from memory resistor. The first device that was developed in the Hewlett-Packard labs consists of it's a two-terminal device. One is anode, another is cathode, top or bottom electrode. Between platinum electrodes, titanium dioxide, doped and undoped layer. The width of the doped layer is W, the total length of the device is D. All these are in nanoscales. And when voltage is applied, the boundary between both moves depending whether it is in positive direction, let's say not cathode or negative. And when the boundary, for example, if the electric field in positive polarity is applied, the boundary moves, and then the electrodes from doped region became more and more, and the resistance of the region decreases. So it may start from off to on. So depending on the strength of the field or the source that we apply, this boundary move from 0 to D, this boundary with length W, and then the device could have a resistance from R off to R on. R off and R on are resistances depending on the material. Now this is the main structure from titanium dioxide. This is type of memristor, metal oxide memristor. So there are many metal oxide memristors based on titanium, hafnium, niobium, and this was the first memristors. And the good for them is that they can be implemented together with the existing silicon technology. So memristors and transistors could be implemented in the same substrate, on the same so the same chip. We can make chip together memristors and transistors. But since that time, many other devices have been shown that show memristive behavior.
That's a polymeric memristors, memristors based on electron spin, ferroelectric memristors, silicon-based memristors, and others. But my talk will be focused on the first type, metal oxide memristors, not because they're historically first, but because of their application together with the standard electronics devices. So the resistance of the memristor is also known as memristance. Could be expressed as derivative of voltage with respect of current, you see, and if we choose, because voltage is the rate of change of flux, and the current is rate of change of charge, memristance is the derivative of flux with respect to the electric charge. So if we have flux charge characteristic, we get the slope of this characteristic at given point. The tangent on this slope is exactly equal to the memristance. And from here, we may conclude that the memristance and the resistance have the same dimension, so they're measured in ohms. Opposite the memristance is memductance. Memductance gives connection between current and voltage. There are several important properties of the memristors. Memristor behave as memory and switch. The main properties are memory and switching properties. It is defined and state-dependent Ohm's law. So Ohm's law depends on the state, and the accumulated charge play a role on the state in this case. The charge flux characteristic, or state flux characteristic, because charge play a role state, are very similar one to another, and they are called fundamental characteristic of memristors. Ideal memristor refers to the perfect idealized version of memristor, and becomes, according to the original mathematical framework, without any practical limitations such as parasitic effects. And it is described by two equations. First, giving the voltage current relationship, but through state-dependent memristance. So memristance depends on charge, and the second one is rate of change of the charge respectively the state, that is equal to current. So the two equations that describe the memristor. This is the important. So memristor is more complicated device, so it's described by two equations, and from here we may conclude that the memristors need more specific modeling. So the modeling is not so simple like the basic elements. A generic memristor refers to a broader or more flexible category of memristors. Memristor systems accomplish such a behavior, and it's originally conceptualized by Leon Chua, and practical devices that exhibit memristic behavior, but any deviate from an ideal theoretical model. It includes any device that demonstrates relationship between flux and charge, and generally system where resistance depends on pulse voltage or current. So resistance is state dependent. By the way, I missed to mention that the state here is the rate is the ratio of for this titanium dioxide memristor, ratio of length of the dot region with respect to the total region. So this plays a role of the state it's proportional to the charge, accumulated charge in the device. Now, current voltage relationship of Memristor is a pinch hysteresis loop. So if we apply sine wave voltage source to the Memristor, the voltage current relationship is well-known pinch hysteresis loop, and depending on frequency, the area decreases. The area of the loop decreases, increasing the frequency, and this is a fingerprint of the memristors. Now I'm going to talk to the several properties of memristors: the DC IV curve, memory properties, switching properties, operating modes, activation thresholds, passivity and nonlinearity. So I'll say some words about any of these properties. The DC IV curves of the ideal memristor consist only at point 00. It can be observed very easy, and you may find out that only at voltage and current 0 DC regime exists. Otherwise, if we have voltage, for example, here constant voltage, then current, and for example, let's charge flux characteristic is cubic. Then in this case, we may calculate the charge, and then the current as a rate of change of charge. So it has this form. So only at the origin we may have DC regime. So DC IV curve exists only at the origin. Now about the memory properties, the most important properties. The memory properties are related to the accumulation of electric charges in the structure and their retaining after the voltage is turned off. The most important property. When the voltage is off, the source is off, the resistance or memristance of the device stays constant. For example, if we have piecewise linear charge flux characteristic, at every slope, the memristance has concrete value. So these are the memory. So memristance has for every interval, for this interval, for example, this value of the memristance. Also, if we apply sequence of pulses with between 0 and 1, the memristance, for example, from off goes to on state, and the state variable goes from 0 to 1. And the moments when the value of the pulse is 0, the memristance state stays constant, the memristance stays constant. So these are memory properties of the memristor. Switching properties are related to the variation of the memristance between R on and R off, owing to the applied voltage. i.e., the memristor behaves as an electronic switch. So switching the memristance between its minimal and maximal values, applying sequence and voltages between minus and ones, is presented in this figure. So now voltages are between -1 and 1. And then in this case, memristance changes from R on to R off, and state changes between 0 and 1. There are two main modes of operation of memristors: soft switching and hard switching modes. Soft switching mode is when the state variable and the corresponding memristors do not reach their minimal and maximal limit values. So the memristance goes not to the R on and R off, but close to them. And in this case, we have the pinch hysteresis loop, and the flux charge characteristic is single valued, monotonically increasing characteristic. In CASS switching mode, the state variables and the corresponding memristors reach their limit values. And then the respective current voltage characteristic is a non-symmetrical curve, very similar to those of the rectifying diodes. The corresponding state flux and charge flux characteristic are multi-valued curves. Important in the CASS switching modes, so-called boundary effects that are very difficult to model. What means boundary effect? Means when the state variable has a value of unity and the voltage continues to increase, the state variable must stay at value 1, should not increase anymore. After changing the direction of the applied voltage, when the voltage starts to become less, the state variable decreases. And vice versa, when the state variable has value 0 and the voltage continues to decrease, then the state variable should remain 0. And after increasing the polarity, when the voltage increases, the state variable starts to increase. The more interesting property of Memristor concerning the so-called activation threshold. This is a specific level of applied voltage. Beneath this level, Memristor operates as a normal resistor. Above this level, it operates as a Memristor. So sometimes we use this property to adjust the operating range of the Memristors. When we need to operate as a resistor, we put it below the threshold voltage, and then it is like resistor solder you see in the first case stays constant. In the second case, when voltage increases the threshold, it operates as a Memristor. The important property is passivity. Memristor is strictly passive element. The fourth element, passive, like resistor, inductor, capacitor, this is the fourth main passive element. It consists, in contrast of the inductor and the capacitor, the Memristor could not store electric energy. You know, inductors store magnetic energy, capacitors store electric energy. Memristor could not store. However, Memristor could store information as a form of its memristors, respectively charge. The information is stored in the memristor as the value of the memristors. Of course, Memristor is non-linear element. When we apply sine voltage, the current is non-sinusoidal, and the current voltage relationship is pinch hysteresis. The potential application of Memristors, a very most interesting application of Memristor is synaptic behavior of the Memristor. You know, the synapses are connections between the axons of a given neuron to the dendrites of another neuron, so they're connected through synapses. And synaptic connection of the biological neuron have a state-dependent conductance. So every biological pulse alerts the conductivity of the synaptic bonds, and in this way, the strength of the synaptic connections, like the membristors, changes proportionally to the voltage pulses. So the strength of the synaptic connections changes proportional to the amplitude of the time duration of the nerve pulses. But for the memristors, the memristors change proportionally to the voltage pulses. So in other words, the biological synapses have memristic behavior, and the memristors have synaptic properties. One very promising application of the memristor is based on memories. The disadvantages of the nowadays flash memories and motivation for application of memristors are the following. The flash memories could not be scaled down than 20 nanometers. comparatively poor retention time between 10 on power 4 to 10 on power 6 times, low switching speed, comparatively high power consumption. Advantages of the potential application of memristors are non-volatile memories of the memristor, so its state depends on the last value of the charge. So when we remove the field, we remove the sources, the value of the memristor stay constant. So the memristors are, as I said, comparatively could be applied to the same substrates like conventional electronics. So also they could be scaled to nanometers, very low dimension, and because they're non-volatile. So when we remove the source, the memristor stays constant, very low consumption, low power consumption, and this makes the memristors very promising for memory applications. Now I'm going to switch to another point, the things related to my current research, modeling of memristors, and this is not too interesting for the audience probably, but because this is what I'm working, I use maybe several minutes to tell exactly what are the main aim of the work that I and my group doing. And in case somebody is interested, may contact me and the people of my group in order to cooperate in this direction. As I told you, Memristor is more complicated device described by two equations: voltage-current relation or current voltage, and state variable, the rate of change of state variable. So x dot k constant, current I, and all this f is called in the models window function. So it is used to bound the states between 0 and 1. So without such a function, we couldn't bound the states between 0 and 1, and the model could not work properly. So we need somehow these window functions, and in many models, and especially models that we are doing, we are trying to choose smart way to choose corresponding window functions in order to get better models. In classical models, I call classical models, standard models, there are Strukov-Williams and Joglicher and Biolek. In these models, the window functions has a corresponding form where STP I is the current, is a step function. The main disadvantage of the step function that is not continuous at point 0. So in case of mathematical operations, due to this, may have some problems of simulation. So these are the step functions for different models. Okay, this is the Biolek model. One important model is Leptonen-Leicht model. When here in the second equation, include voltage, not current, voltage, and this makes the model applicable for high frequencies. So this is more complicated model, but applicable for high frequencies. All these models were for titanium dioxide memristors. I'm going to present also two models, one for hafnium dioxide. This is this model. I put some numbers of them. This is K7, and for tantalum oxide memristor, model K9. K9. This is proposed by Ascoli and Teslov, Professor Chua. All these out of Memristors models, the main idea here is to replace the step function with this one, that is continuous differentiable function, and depending on parameters, of course, vary between 0 and 1. And so with this function, we avoid some problems in the simulation when simulate the Memristor behavior. So we have, based on this function, we propose several models: modified model A11, A12, A13, B1, and B2. There for especially for tantalum and halcyon models. All these models are okay. This is model based on electron and LIGO. This is A7 modified model. All these models. Okay, this is the continuous function STPP. So see again, this is between -1 and 1, but it is continuous differentiable and could be used for better presentation of the for avoiding numerical problems when simulate the Memristor behavior. So there are a lot of models also that I developed in my team. Here I presented only several ideas, what type of modifications I did for some known models. Of course, I have some other models, author models, so this is not the main topic of this talk. But what we observed that is missing the somehow the criteria for comparing the models. In many papers, I found different criteria, but it does not say exactly what given criteria means. So I tried to generalize all existing criteria that were used, and for example, and do definition. Many of the criteria are quantitative, not qualitative. For example, this qualitative signal levels that work, but nonlinearity, expression of boundary effects, representation of switching, model accuracy, activation threshold, model tunability. For example, it is the ability of the Memristor model to be adapted to a specific experimental voltage current characteristic while obtaining a minimum non-mean square error between the measured and simulated characteristic. Correct representation of voltage dependence of non-linear ionic Doppler drift, especially for metal oxide Memristors, ability to express symmetric voltage current characteristics, model modes of operations, representation of state float characteristic, complexity, operating frequency, the three ranges of frequency, they're accepted between 0.5 and 1 kilohertz. These are low. Middle frequencies between 1 kilohertz and 100 kilohertz. The high frequencies higher than 100 kilohertz. And this is the comparison between the models. These are the between some of the models. These are the known models, standard models. These are models that auto models developed by my team. This is tantalum and half-cube model and the corresponding modifications. So I'm talking only about modifications. Of course, you could not get better performance everywhere, but the main idea behind the models that we propose work for high frequencies to be comparatively low complexity, low number of elements, and the simulation time to be comparatively good with respect to the others. All these things are summarized in my book, Advanced Memristor Modeling. This is an open source book, you may get it. And that time when this was published in 2019, so 6 years ago, in this book, I presented some models, but the main conclusion was the good accuracy, close to Leptonian LICO model, because Leptonian LICO model is very complicated, with very good accuracy. We try to develop models that are not so complicated, but with good accuracy, low complexity, less elements, high operating frequencies, good switching properties to be used in Memristor, and reduced simulation time. Later on, maybe last year, my team developed a model for first with parasitic parameters. I obtained that several authors try to use parasitic parameters. They obtained that their role is negligible, but in some cases, especially for high frequencies, the capacitors play a role, and inductors, and also these sources correspond to the shift of the origin of the characteristic of the pinch hysteresis loop with respect to the origin. So this describe these parasitic effects. So using the model with parasitic parameters, we describe better the behavior of the Memristors. So this is the work is here, presented here. And now I'm going to skip the mathematical description, but well, no, the GNOME Memristor that is developed by GNOME company. We developed two models to compare them. Let's say this is called B6M and B6 par. This B6 par is model that includes the parasitic parameters. What we did, we got GNOME Memristors on chip, so it is a free chip that everybody can buy with different type of Memristors produced by this company GNOME. And we did a simulation, and we got volt-amp characteristic, this pinch hysteresis characteristics, took voltage and current on oscilloscope, on numeric oscilloscopes, and then based on the points, we adapted the model. So we found the parameters of the model. So this is called tuning of the Memristor model based on the minimal good square error between the measured and estimated values. So this is how the program works. At the end, we got the values of the model parameters. So this is very time-consuming optimization procedure to get the parameters. Okay, when we adopt a given Memristor model, we do this, and we did it for the GNOME Memristor. One of the types of the GNOME Memristor. There are several, I may say many on different chips, but for those that we got, we have the precise model. And this is how the procedure, optimization procedure works. So how at the end we got the parameters that describe the model, and then the experimental for model BM. This is the difference between the experimental volt-amp and obtained volt-amp characteristic. You see very, very close. They're very close. So tuning the model means to find the parameters which fits the model to the data. And after finding the parameters, we develop what I think is very useful. We developed LT-SPICE model of the Memristor, complete LT-SPICE, and I have a library with LT-SPICE model. This is the link is somewhere here, so everybody can download the models and can test it in LT-SPICE. And especially, this is the comparison between the non-Memristor. It has corresponding model, which is very complicated. Given our formulas, we applied it. K3 and K5 and B6 and B6R, the new models, and see the K3 is very simple but low complexity, but accuracy is average, the operating frequency average. So these models relatively better performance that we develop, especially model with parasitic parameters that works well for high frequencies. So the main advantages of B6M and B6R are presented here, especially as I told, this is the comparatively low complexity, activation thresholds included, simple window function, application for high frequencies. And okay, this is the GitHub address of the LT-SPICE library. We use several symbols for Memristors, this one, but also we use this top and bottom electrode, 2 terminal. Also, we use 2 terminal, but we left one more for the states. So if one want to measure states, we get the signal from here. And there is the complete description in this library, how to get the model, how to install it and to use in schematics and how the schematics works. So I got many questions for different, especially PhD students that start to work with Memristors, how to utilize these models. Of course, this is more or less for educational purposes, but based on this modeling, the people can develop their own cadence and other Memristor models. And now I'm going to move to the last part, application of Memristors. There are 4 main important applications: Memristor-based memory, Memristor-based neural networks, Memristors like circuits and configurable devices. I'll skip this, these 3 of them, and I'll especially talk to neural networks because my interests are there. But because configurable device, because Memristors could change, it could play a role as a switch, and because of this, we may get with the same schematic many devices depending on the value of the Memristors. So we may have different filters, memories, of course, but again, I'm going to talk to neural networks. First, we started, let's say 10 years ago, how to model synapses with single Memristors, with several Memristors, at least 2 Memristors. You may see here 4 Memristor bridge schematic, but the idea is to use as less Memristors as possible. The most simple way is to use single Memristor, but with single Memristor, we couldn't model the negative synaptic weights, because in a neural network, you know that the weights, called synaptic weights, could have positive and negative values. So negative synaptic weights couldn't be modeled with single Memristor. So there is a way that we apply this and did this modeling. But we started with 2 Memristors, 4 Memristors. And you see this is a neural network, input signals, hidden neurons, output neurons. Here, for synapses, we got Memristors because Memristors normally are in the crossbars. For synapses are taken, for synapses, we take Memristors from crossbars, and input and output neurons we model with not model, we realize with zooming elements, op-amps, and other Memristors or resistors depending on the application. But based on review, let's say 10 years ago, we observed that the authors do not present complete schematics. They give principal schematics, but they do not present complete schematics. They do not present SPICE models in the papers. At least we couldn't find. So we decided to do step-by-step SPICE implementation of neural networks, starting from simple to extend it, and give the people to develop their own neural networks based on Memristor, based synapses, consisting of synapses based on Memristors and most transistors. So these are some papers that publish in this area. Of course, synapses realized in different ways. I'm going to skip this. I'm going to these slides where we say the main idea. This is a single neuron. This is the summing element, synapses, signals. This is the activation function and output. Maybe everybody knows that this is the main structure of the neuron. So signals held by synaptic weights, summator, and the activation function and the output. So what we did is, because of op-amp, these memristors, the signals goes here with negative values. So with these memristors, we realize negative synaptic waves. In order to realize positive synaptic waves, we divide the input signals in two groups with negative synaptic waves, with positive. This with positive, we use another op-amp for those, and then do summation, and on this way we may realize synaptic waves with positive and negative waves, and these are the value, the variable input output variables. And this is the output of the summing element here, this one, and this is the activation function. This is logarithmic activation function with a block. First, we start to realize with a block, but then, okay, this is the SPICE realization. SPICE. This is the output activation function as a block, but it was not complete realization because we do not need block. We need the schematic. We find a good schematic for this. Yes, this is implementation of activation function with two transistors and this source, and depending on the value of this source, we have either logarithmic or signals. Without this, we have tiniest sigmoidal function. And these are LT-SPICE realizations of this logarithmic activation function. And these are the differences between the activation function realized this realization with most transistors, and the idle one realized by formula. So you see very small difference. So in this way we have complete transistor and memristor implementation of a single neuron, and it is, for example, not single neuron, but let's say this is multi-layer network. These are signals. First layer consists of two neurons. Second layer consists only output layer of one neuron. And both neurons uses the same signals, but the synaptic weights are different. And for these principles here, the corresponding SPICE realization is this. So these are the summators, and this is the activation functions and summators. So these are two input neurons. This is the output neuron. The synapses are here, input signals are here. But if we extend this, this is the complete schematic. of this simple two-layer network with two neurons in the input layer, one output neuron. These are the corresponding activation functions realized by with transistors. Let me see the time now. Maybe I'm completely running out of schedule. Anyway, now what we did check of the schematic whether it works like what is expected. In fact, it is correct. We did MATLAB simulation and simulation. So these 6 signals got 6 levels. For example, there we have one time interval for this of the 6 input signals, then 0, then another combination of input signals, and the corresponding input of the input signal of the output activation function is this, and the output neuron is this. And comparing all these values with MATLAB, we see very close MATLAB calculations, which are based on formulas, very good coincidence of the results. Now we apply this for the new model with this was with the models that I talked 10 years ago. For the 6 or 10 years ago, this is for the last model with parasitic parameters. For the GNOME Memristor, because we developed a single schematic on board, we tested it. We made the SPICE model and we made the MATLAB model and calculated all the values, did comparison. So this is the principal schematic. In fact, this is the calculation of the time that we need in order to adjust the memristors. And this is based on the formula, based on the model B6. We calculated the length of the impulse that corresponds to the corresponding value of the memristors that we need. So this is the precise calculation based on the model. So adjusting the weights, we got the. So this is how we adjust the memristors with series of pulses, or one pulse with the corresponding value as is described here for every memristor. To apply this in real multi-layer network, we need scaling the output of every, for example, hidden neuron, in order input signal for the next neurons to be in the range to work below the threshold. So we scale it appropriately and then rescale it. So we need one more op-amp for every neuron in order to do this scaling to ensure this after the end of the activation function, in order to ensure the matching of the corresponding hidden neuron, and here is the output neuron, for example. And this is the corresponding schematic of the whole memristor, of the whole neuron, of one neuron, and of course the difference between the activation function based on real device, real transistors, and activation function based on this one, activation function based on calculation. And okay, and we calculated for this simple case, we developed 6 cases for 6 different combinations of input signals and corresponding weights, synaptic weights, and the memristors that corresponds to these weights are calculated. And then they are applied, and we made a check between the behavior of the schematic and the MATLAB again, so to check whether the performance of the network is the same. And okay, this is the full schematic based with Memristors with parasitic parameters, and the corresponding measurements are done. So this schematic we realized on the board also. So we have complete for this simple schematic 3 neurons. Yes, 3 neurons with 6 inputs. 6 inputs, 3 neurons, 2 in the hidden layer, 1 in the output neuron. And based on this, we did the comparison and find out pretty good coincidence of, again, 5 cases of the input signal 1, 2, 3, 4, 6. So for 5 cases, we did the 5 cases, means 5 different combination of input signals. We did the check. This is the schematic in MATLAB, in Simulink that we use to compare the results. And for these 5 cases, the comparison of the results. The weights and memristances for both memristors with parasitic and without parasitic parameters. So, as a conclusion, I may say that I presented this relatively short talk, basic information about memristors, the structure, principle of operation, main properties of the memristors, some models, classical and modified, to give an idea of modeling and what especially I'm doing in my current research. Literature review of main publications about neural networks based on memristors. In all these references, you show that there is no real schematics. People do not show schematics. Simply they present results, but without schematics. So then we decided based on this to give complete memristor-based neural network implementation in LT-SPICE, just for simple neurons, but we have for more complicated networks. In fact, we have realization on board for simple neurons, but we simulated very big networks. So, and we did analysis and comparison, and it shows that based on different models, we got comparatively good, even very good coincidence of calculated results based on simulation in SPICE. So this was everything. Thank you very much for your attention. Now it's time to have some questions.
So thank you very much, Valeri, for your nice talk. So we are waiting for questions. Please do your question as soon as possible. So waiting for other questions. I have one. So so nowadays there is a big effort in the research and development of 3D chips. And so doing that, can you comment about the possibility to have one tier or one layer with technology dedicated to memristors?
I'm not specialist in chip design. This I'm going to start with this. So I'm not. Right. I'm in electronics, but not in chip design. But what may I say that it is possible? It is possible, and the memristor has their role, their place. It's compatible with standard electronics, and if it is done on smart way, of course we may get very, very good results. What I say from my experience and what we are doing is that combining memristors with standard electronic, based on simulation, of course, and now we have some measurements. It works very, 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 very well. So the main advantage is low power. They do not use low dimensions, low power due to the non-volatile behavior, and it is worth to. It's again not my research area, but it's worth to invest in this. And I'm sure that this is done somewhere, maybe not published, but it is done somewhere, because this is, as you said, very promising, and this is there are many good applications can be done with this.
Thank you very much. I'm seeing no questions today, so I would like to thanks to Valeri for the nice talk, a nice presentation, and then we are closing the 2025 season of CASS Talks. So it was several years that we are organizing this, and you can find in the YouTube channel more than 150 talks till now. And so now we are going to have a break in January, February, and then in March we restart. We have already some talks that are defined for March next year. So I wish you all a great end of the year, very nice Christmas, and I hope to see you all next year for the 2026 season of the CASS Talks. And I hope also to see Valeri in person soon. And
Thank you.
Yeah, so thank you very much again.
One word only, Ricardo, one word.
Yes.
It was interesting for me to find out, you told me about these CASS talks, and if you send me the agenda where to find it, I'll be glad to follow the talks with pleasure.
Yeah. So when we talk is defined with the abstracts and so on, in the YouTube CASS Rio Grande do Sul channel, it's done the announcement, and but we hope to do the announcement of the next talk soon, because as I told you, there is some ones that are already defined for the start of the 2026 season. So bye-bye to all you, and have nice holidays for the one that will travel, nice trips, and so see you soon.
Bye-bye, and nice holidays to me as well.
Bye-bye.
It was my pleasure. Bye-bye.
Thank you very much.
Bye.